Welcome, my friends! In this video, we will be introducing discrete probability distributions. Recall the distinction between discrete and continuous variables, which I have discussed in other videos. Both are examples of quantitative variables. Discrete variables can take on only certain values on the number line, typically the whole numbers. This might be something like the number of pets a student owns, or the number of customers who enter a store in an hour. On the other hand, continuous variables are not restricted to certain values on the number line. All decimals between any two numbers are allowed for continuous numbers. Examples include height, weight, and time. These are all variables that don't need to be expressed as whole numbers. We can include any decimal between whole numbers too. A probability distribution describes how likely all values of the variable, sometimes called the random variable, are to occur. The focus of this video will be on discrete variables. Here is an image to help you better understand the distinction between discrete and continuous variables. We have two variables that each range from 0 to 11. If the variable is discrete, that probably means only the whole numbers are allowed, such as 0, 1, 2, 3, 4, all the way up through 11. Technically, you don't have to have just the whole numbers to have a discrete variable. You could have, say, every half number, such as 0, 0.5, 1, 1.5, etc., but the most common case is the whole numbers. The main thing to know is that every single decimal between 0 and 11 is not allowed, only certain values. For a continuous variable, any decimal or whole number between 0 and 11 is allowed. We are not restricted to just certain values on the number line between 0 and 11, which is what makes this a continuous variable. To make sure that you understand the distinction between discrete and continuous variables, consider these four examples. Take a moment to pause the video and see if you can determine if each variable is discrete or continuous. Alright, the number of A's a college student earns in a semester is a discrete variable. The student could either get 0, 1, 2, 3, 4, or perhaps even more A's, depending on how many classes they are taking. And we are restricted to only the whole numbers, which makes this a discrete variable. The number of hours a high school student sleeps in a night is continuous. Sleep time is not restricted to only certain values. Someone could sleep 8 hours, but more likely they will be somewhere between two whole numbers, like perhaps 7.5 hours. Additionally, we aren't restricted in our decimals. We can have any decimal value for the number of hours of sleep, which makes this variable continuous. The distance between any two random cities is continuous. Distance might be measured in miles, and we aren't restricted to the whole number miles. There could be perhaps 100.37 miles between two cities, which makes this variable continuous. The number of cars sold by a car salesman in a month is discrete. The salesman could sell 0, 1, 2, 3, or even more cars in a month, but it wouldn't make sense to sell a partial car. We are restricted to the whole numbers, so this variable is discrete. Let's take a look at what a discrete probability distribution looks like. Let's consider the number of A's received by a college student in a semester. To keep things simple, let's limit this to anywhere from 0 to 4 A's. Of course, some students might be taking more than 4 classes, so the total number of A's could be more than 4. But for simplicity's sake, let's assume that the maximum number of A's for a student to earn in one semester is 4 for this example. The table shows the possible values for our variable, which range from 0 to 4 A's, as well as the probability of an individual getting the specified number of A's, perhaps gathered from the university's records. The most common number of A's received by a student in a semester is 0, which applies to 50% of the students. Only 3% of students earn 4 A's in a semester. As mentioned earlier, the number of A's received is a discrete variable, as we can only have a whole number quantity of A's. We can also count the number of A's a student earns, which is usually an indicator that the variable is discrete. Notice that all probabilities in the distribution sum to 1. This will always be the case, as all of the outcomes must make up 100% of the probability. You may at some point be given a distribution like this one, with one probability missing, in which case you will need to solve for the missing value by determining what number forces all of the probabilities to sum to 1. We can ask probability-related questions based on the discrete probability distribution that are generally quite easy to answer. For example, what is the probability that a random student earns exactly 2 A's? Well, just look at the table. The probability x is equal to 2 is 0.1, meaning that 10% of students earn exactly 2 A's. How about the probability that a random student receives at least 2 A's? At least 2 means 2 or more, which includes the outcomes 2, 3, and 4. The probability x is greater than or equal to 2 can be found by adding up the corresponding probabilities. 0.1 plus 0.07 plus 0.03 is equal to 0.2. The probability a random student receives at least 2 A's is 20%. To find the mean of a discrete probability distribution, oftentimes called the expected value, simply multiply each outcome by the corresponding probability and add the results together. In formula form, we write this as mu equals the sum of x times p of x. For our example, we have mu equals 0 times 0.5 plus 1 times 0.3 plus 2 times 0.1 plus 3 times 0.07 plus 4 times 0.03, which is equal to 0.83. On average, a student receives 0.83 A's in a semester. Of course, that value is not a possible number of A's for a single student, but you could view a student as earning somewhere between 0 to 1 A's on average. Consider another example related to the lottery. There might be a 99.9% chance of losing the lottery, in which case you make $0. Perhaps in real life, this value might be negative, but let's assume someone gave you a lottery ticket. The chance you win the lottery, which let's say is worth $1,000, is 0.1%, or 0.001. To find the expected value, or mean, we would take 0 times 0.999 plus 1,000 times 0.001, which gives us $1. That means you would make $1 on average for every time that you play the lottery. Sure, most of the time you wouldn't make any money, but occasionally you would win $1,000, and the average per game winnings come to $1. If you have to pay more than $1 to get a lottery ticket, it isn't a great strategy to continue playing games to try to get rich. Let's look at an example related to a game of chance. An urn contains 10 balls. 3 are blue, 6 are yellow, and 1 is black. You are playing a game where you randomly draw 1 ball from the urn. If the color is blue, you win $10. If the color is yellow, you win $1, and if the color is black, you lose $40. We can summarize the results of the game in this table. The color of the ball that you draw could either be blue, yellow, or black. If the color is blue, you will win $10. If the color is yellow, you win $1. And if the color is black, you lose $40, which we represent by negative 40. The probability you draw a blue ball is 3 out of 10, since there are 3 blue balls and 10 balls in total, and we assume that there is an equal chance to choose any of the 10 balls. The probability you choose a yellow ball is 6 out of 10, and the probability that you choose a black ball is 1 out of 10. What is the probability that you will make money from playing this game a single time? Well, that's kind of like asking what the probability that you make more than $0 is, or the chance that x is greater than 0. The only outcomes where you win money are where you draw either a blue or yellow ball. So add up the probabilities associated with those two outcomes. 3 out of 10 plus 6 out of 10 is equal to 9 out of 10, or 90%. There is a 90% chance that if you play this game a single time, you will make money. Just looking at this percentage alone, the game seems like it might be worth playing. 90% of the time, you are going to make money. But 10% of the time, you are going to be losing $40. It might not be clear if the frequent gains will outweigh the uncommon losses. We might want to know, in the long run, can you expect to win money by playing this game over and over and over? To determine this, we will calculate the expected value, which is equal to 10 times 3 out of 10, plus 1 times 6 out of 10, plus negative 40 times 1 out of 10, which is equal to negative 40 cents. This means you can expect to lose about 40 cents on average per game if you play this game many times. Sure, most of the time you're going to be making money, 90% of the time in fact, but the small percentage of the time that you lose money outweighs the gains. More frequently, games of chance are weighted in a different way, such that you lose money the vast majority of times, but there is a small chance of winning big. In either case, always calculate the expected value to see if it is financially worth your time to play the game. There's practically always a negative expected value for the player, but even such, it's nice to know exactly how much that value is. Let's try one more example related to a business application. A company sells a 5-year insurance policy. A man purchases a policy for $15,000 on his 65th birthday. In reality, typically the insurance premiums are made monthly, but to simplify this example, let's assume that this individual purchases the entire insurance policy upfront for $15,000. The death benefit for the policy is $100,000, meaning if this person dies in the 5-year period, the beneficiary, probably his wife or someone else, will get $100,000. Based on the actuarial tables, the probability of death is known for a male between 65 and 69 years old and is displayed in the table on the right. The chance that any random 65-year-old male dies sometime between his 65th and 66th birthday is about 1.6%. For between 66 and 67, it's about 1.71%, etc., all the way down through 69. Let X represent the profit of the insurance company. We want to know how much the insurance company is expected to profit for each 65-year-old man who signs up for a 5-year insurance policy. We know that most of the time, when the individual survives, the insurance company is going to profit big. They will pocket the entire $15,000. A small percentage of the time, the insurance company will lose big. They will have to pay out the $100,000. The expected profit is somewhere in the middle. We can create a table that represents the discrete probability distribution of profit for this company. Let's start by calculating the profit for an individual who lives through the 5-year contract. In this case, the person has not died, so we are in the no column for death. The insurance company will profit $15,000 in this case, as they will be able to simply pocket the entire price that the man paid for the policy. The profit earned when the individual dies is a little bit more complicated to calculate. At first, you might think that this should just be negative $100,000, as the insurance company has a payout of $100,000 in the case that the individual dies. But you must also account for the $15,000 paid for the insurance policy in the first place. So if the individual dies, the company will make $15,000 for the insurance policy purchase price, but will also have to pay $100,000 to the beneficiary of the policy. This makes for $15,000 minus $100,000, which is equal to negative $85,000 profit in the event that the individual dies. Let's now calculate the probabilities. The probability the individual dies, which could be represented as the probability death is equal to yes, or the probability that X is equal to negative 85,000, is just the sum of all of the probabilities in the age table. The chance that a 65-year-old dies in any of the 5 years he has the policy is the sum of the 5 probabilities, since each year is mutually exclusive. When we add the 5 numbers together, we get 0.0994. There is a 9.94% chance that a 65-year-old man dies within 5 years of taking out this insurance policy. On the other hand, the chance that a 65-year-old does not die in the 5-year period is just the complement of the probability that he does die. So if there's a 9.94% chance that someone does die in the 5-year period, there must be a 90.06% chance that they do not die, or 1 minus 0.0994. This is the value that forces all of the probabilities in the table to sum to 1. At this point, we can calculate the expected value. Negative 85,000 times 0.0994 plus 15,000 times 0.9006 is equal to $5,060. This company can expect a profit an average of $5,060 for each 65-year-old who purchases a 5-year insurance policy. Alright, my friends, that wraps up our video introducing discrete distributions. We will be exploring more fun and exciting statistical topics, so make sure to check out our other videos.